Assalamu alaikum wa rahmatullah. Good day, everyone. I welcome you all to our maiden lecture on medical physics, MLS 3205. The topic is Blood in Motion 1, and this is the first week lecture. I, the presenter, am Shuaibu Muawiyah Salim Kano, today being 4th May 2024. First of all, I would like to apologize. You may notice some irregularities in my speech. This is because I am a bit feverish today. Second of all, I am welcoming you all and then congratulating you for being promoted from 200 level to 300 level. I pray that Allah subhanahu wa ta'ala grants us a beneficial knowledge. Now, the first thing we will consider today is learning objectives. These learning objectives are specifically for this week, not for the entire course. Every week has a learning objective. Let's see the learning objectives for this particular week, the very first week of our lecture. At the end of this lecture, students should be able to, these are activities that you should be able to do after attending class or after watching this video. Okay, the first thing you should be able to do is explain and solve problems, mathematical problems, on the kinematics of human blood circulation and pulse. You should explain human blood circulation using kinematics. Kinematics is the study of motion, is a branch of mechanics. In physics, we have a study called mechanics, which is the study of motion. Now, this study of motion is divided into two. We have dynamics, we also have kinematics. Dynamics is when you are considering the forces that cause the motion, the masses of the object and the forces that cause the motion. But if you have no regard to the forces causing the motion, neither are you considering the masses of the object, you are only interested in the object's displacement, the object's distance, velocity, acceleration, time taken, then this study is called kinematics. This is what we will be doing. Although you will see the word dynamics because part of this course, later in this course, we will also study blood dynamics as well. The second thing, which is also the final, is you should be able to derive the continuity equation. The continuity equation. After deriving this continuity equation, you should be able to use it to solve problems on blood speed, meaning to calculate blood speed and also the flow rate. When we say flow rate, we mean the amount of blood, the volume of blood passing through a given point in 1 second. We call that flow rate, and with the help of the continuity equation, we will be able to calculate the flow rate. So after watching this video, these two activities, they are actually four. I just summarized them into two because each one you take is twofold. Number one, say explain, that is one, and solve, that is two, and then number two, say derive the continuity equation, that is activity 3, and then use it to solve problems, or there should be the word 2 here. Use it to solve problems on blood speed and flow rate. So you have 4 activities in all. At the end of this lecture, you should be able to do all these activities. Now, as an introduction, we explain blood dynamics. Blood dynamics is the study of the movement of blood through the circulatory system. And as I mentioned earlier, in dynamics, we are concerned about the forces causing the motion and, of course, the pressure exerted by the blood or on the wall of arteries and veins as it flows through them. The physics of blood dynamics is governed by several important factors, including the properties of blood itself, the structure and function of blood vessels, and the forces. You see, this is what we are talking about, and the forces that act on blood as it flows through the circulatory system. Now, in this lesson or lecture, we will learn physics concepts related to blood dynamics, which include blood circulation and pulse and flow rate. Now, as part of the objectives of this course, this week lecture, I said we will explain kinematics of blood circulation. So here is the explanation here in brief. Kinematics is a branch of mechanics that deals with the study of motion of objects without references to their masses or forces that cause the motion. I already explained that, meaning you do not consider the forces that cause the motion at all, and you do not consider the masses of the object. You are only interested in the distance covered, the time taken, the velocity, the speed, displacement, all these parameters, okay, but no mention of force, no mention of mass. So here they said displacement, velocity and acceleration are all studied in kinematics. That is in general. This one is not just peculiar to blood. This is an introduction to that affects all matter in the universe, any object, not just blood alone. Now we will be specific. Now they say the kinematics of human blood pulse refers to the movement of blood through the body's circulatory system, which is controlled by the pumping action of the heart. We know it is the heart that controls the circulatory system. It pumps the blood right there, and then the blood pulse can be expressed in terms of its velocity, acceleration and displacement with respect to time. When we get to problem solving, you will see exactly what this is all about. The human blood circulation system is an essential part of the circulatory system responsible for transporting blood from the heart to the various organs and tissues and returning deoxygenated blood to the heart for oxygenation. This means the blood is treated with oxygen. When it is treated with oxygen, we call it oxygenated blood. Now, the primary function of the blood is to transport oxygen, nutrient to all body parts. Now, after the transportation, the blood will now be devoid of oxygen. When it is devoid of oxygen, meaning when it has delivered oxygen to all the body parts, it will now be without oxygen. If it has no oxygen in it, we call it deoxygenated blood. By this D, this prefix, we mean oxygen is removed from it. So it comes back to the heart again for oxygenation. The system consists of the heart, blood vessels, and blood. The heart pumps blood into the arteries. We will see all this in a diagram. They say that the heart pumps blood into the arteries, which carry oxygenated blood, meaning blood treated with oxygen, and it carries oxygenated blood away from the heart to the rest of the body. The blood then moves through the capillaries, exchanging oxygen and nutrient, exactly what we said. Finally, the oxygenated blood is transported through the veins. The deoxygenated blood, that's after exchanging nutrient. The deoxygenated blood is transported through the veins back to the heart, where the cycle starts again. Now, with the aid of a diagram, we can understand this kinematics easily. Here is a diagram. Here, you can see that this is where the heart is. This is the heart. And the heart has two ventricles. You have the left ventricle here and you have the right ventricle, and it has two openings at the top, which are called atrium. Each one is called atrium. You have the right atrium here and you have the left atrium here. Now, after transporting, when the blood has transported oxygen and nutrient to all body parts, it comes back to the heart through the right atrium, and then it enters down to the left ventricle, and then the cycle starts, or the pit itself. And that's why they put number 1 here. Now, the blood without oxygen. Let me make this explanation here. Wherever you see green color, wherever you see is blue color, wherever you see blue color, it means what you have there is blood without oxygen, deoxygenated blood. And wherever you see red color, it means oxygenated blood, blood treated with oxygen flows through there. So here we have blood without oxygen and it flows through here, and we see it's given number 2 here, and then you have two parts here. You see it divided into two pathways, and this one, each one is called pulmonary artery. Pulmonary artery, it is the artery that leads to the lung. Pulmonary means related to the lung, and here too you can see this artery leads to the lung, so it's also pulmonary artery. Now, when they lead to the lung, you can see that each lung is given the number 3 because it's the same activity, is the same phenomenon going on in 2. Here, when you inhale air, oxygen gets assimilated, gets diffused into the blood here in the lungs. So the blood that gets to the lung here acquires oxygen, is treated with oxygen, and then you can see that blood with it turns red here to tell you that it is treated with oxygen, and then comes back to the heart through the left ventricle. And this one too, after being treated with oxygen in the lungs, it enters into the heart through the left through the left atrium. Then it goes down to the left ventricle. You can see you have 4 here. This is 3, this is 3. So the left atrium has number 4, and then when it goes down you have number 5, and the heart pumps it through the aorta. Then it comes here. Part of it will go up to the head and the forelimbs. You see capillaries of head and forelimbs, so the blood will go there to transport oxygen and nutrient. And then this one will go down, the remaining part will go down. You see it's still the aorta, going down to the capillaries of abdominal organs, meaning organs of the stomach and the hind limbs. Now after exchanging here, it goes up without the oxygen, because the oxygen from the abdominal organs and the hind limbs, the oxygen get used up. So you have the blood without oxygen coming back to the heart through the right atrium. This one too that goes up, you see, is given the number 7. You see, it goes to our 2 hands, our chest, our head. Then all the organs there, the system we have there, they will use the oxygen and the nutrient, and then the blood will now become deoxygenated, meaning devoid of oxygen, and then it comes down here. You can see 9 here. It goes down to the right atrium and enter. The one that goes down here will also come up here and enter through here without the oxygen, and the cycle repeats itself. This is how blood kinematics is, a human circulatory system. Okay, we can see here that this is so very important. We can see here that we have the blood from the heart, and then it passes through the artery, and then the artery has a branch here we call arterial. Arterial means a branch of an artery, and then after that you have the capillaries. And then you can see that in the capillaries the exchange of nutrients occur until the blood has no more oxygen, no more nutrient, so you have blood without oxygen flowing through the vein. This is the branch of vein and is called venule, and then it goes to the vein here and then goes back to the heart. Arteries, arterial, veins and capillaries network. This is the same thing is going on here. I only put this so that you can see the cross section of the arterial, the branch of the artery. Okay, here are the meanings of key terms, the key terms related to the blood kinematics. Here, the path that the blood flows through. We have the first one here. We have the ventricle is a hollow part or cavity in an organ, e.g. Each of the two main chambers of the heart, left and right. The ventricle, where is the ventricle here? Let's see it here. You see here, down here is the ventricle. You have the right ventricle here, and you have the left ventricle here. Then the next one here is atrium. Atrium is one of the two upper openings of the heart. You see, blood without oxygen, meaning deoxygenated blood, enters into the heart through the right atrium. You see the opening here, right atrium, and then blood with oxygen enters into the heart through the left atrium. Going back again, we have after atrium, what do we have again? We have pulmonary. Pulmonary means having to do with the lungs. Anything that has to do with the lung, we call it pulmonary. So if you go back to our diagram here, you can see this is an artery that leads to the lung. So we call it pulmonary artery. This is a vein. It leads to the lung. It connects the lung to the heart, so we call it pulmonary vein. On the left, you have the same thing. You have pulmonary artery, and you also have pulmonary vein. The pulmonary artery carries the oxygenated blood, and the pulmonary vein carries oxygenated blood. Then we have aorta. Aorta is an artery, is a big artery that when the heart pumps the blood, it leaves the heart through the aorta. Can you see? It leaves the heart through the aorta. So that is it. Then we have the artery. They said a blood vessel in humans and most other animals that takes oxygenated blood away from the heart in the systemic circulation to one or more parts of the body. And then you have the vein. This one, after the blood is treated with oxygen, this is let's say the tube that carries the blood to all parts of the body. Blood with oxygen. That is why they say that takes oxygenated blood. Now, after the body part use the oxygen, and the blood has no oxygen now, is without oxygen, then it flows through the vein. It flows through the vein, and that is why they say any of the tubes forming part of the blood circulation system of the body, carrying in most cases oxygenated, oxygen depleted, meaning without oxygen, or deoxygenated blood towards the heart. But do we have a vein? Let's check pulmonary. The pulmonary vein, does it carry oxygenated blood? Does it carry deoxygenated blood? I think we have. Now, if we go back to the diagram, let's see that. If we go back to our diagram here, you see pulmonary artery. and this is also pulmonary artery. So it's an exception here. It's the only artery that carries deoxygenated blood. We said arteries carry oxygenated blood, but look at pulmonary artery. It carries deoxygenated blood. So this is an exception. We also say that veins carry deoxygenated blood, but when it is a pulmonary vein, it carries oxygenated. Can you see pulmonary vein? Pulmonary vein. Okay, they carry oxygenated blood. This is an exception that we have here. Okay, vena is a Latin word for the word vein. Arterial is the branch of an artery. We saw that in the diagram, but at least let me go back again. Okay, here this is an artery. Then this is the branch of an artery. We call this arterial. Okay, this I think is even clearer here. We have an artery here, and then look at each branch here is called arterial, and when you put the s here, it becomes plural, arterials. Now let's go back. Okay, venule is the branch of the vein, any of the minute veins connecting the capillaries with the larger systemic veins. Okay, the next thing we are going to do is to consider the summary of kinematics equations. These are the equations we may need to solve kinematics problems. The first one is the equation for displacement. Delta x is used to denote displacement, and x final is the final position of an object, and then x initial is the initial position of an object. If you take the final position minus initial position, this measurement gives you displacement. Then average velocity. To get average velocity, you use the displacement you obtain here and the time taken to get this displacement, to have this displacement. So you divide the two, delta x divided by delta t. In other words, if you know the final position of an object, and then you know the initial position of an object, and also the clock time when this x of f is obtained, and also the clock time when this x of I is obtained, you subtract these t sub f minus 1, and then here t sub x of f minus x of I, t sub f minus t sub I. This will give you average velocity of an object. Then instantaneous velocity, meaning the velocity at any given instant, is the limiting value of the average velocity. If you look at this expression, is for the average velocity that we talk about here. So if you get the limiting value of this average velocity as delta t tends to 0, this is also what we call the x dt, meaning the first derivative of displacement with respect to time will give you instantaneous velocity. It will be an expression that you can use to get the velocity at any given time. After 1 second, you can put t is equal to 1 to get the velocity. After 3 seconds, you can put t is equal to 3 to get the velocity again. Then identically, we also have average acceleration. Average acceleration is the velocity, okay, the change in velocity divided by the time taken to make this change, to produce this change. When you do that, you get the average velocity. We also have average acceleration, sorry. We also have instantaneous acceleration. Instantaneous acceleration is the limiting value of the average acceleration as delta t tends to 0. And then we have constant acceleration. Now, when the acceleration is constant, the motion is now called uniformly accelerated motion, because acceleration is not changing. So when the acceleration is constant, we have the following relations. Look at the relations here. We have the average velocity, and average velocity is half into final velocity plus initial velocity. If I know the final velocity and I know the initial velocity, I can add the two and divide them by 2. This 2 is their number. You have 1, 2 velocities, you add them and you divide the result by 2 will give you average velocity. Now if you want to get a change in velocity, this will be the constant acceleration. Remember, acceleration is constant, and then multiplied by the time taken to produce this change in velocity. So when you multiply the two, you get the change in velocity. Again, if you want to know the displacement, delta x, remember, is displacement, is equal to the initial velocity of an object multiplied by the time taken to produce this displacement, plus half multiplied by the constant acceleration multiplied by the square of the time taken to produce the displacement. Again, you can also use this final velocity squared minus initial velocity squared is equal to 2 times acceleration times the displacement. Now here they say, note that if the initial position x naught and velocity v naught are taken at the initial time t is equal to 0, then your delta t is t minus t naught, will be simply just t. So you can say delta t is simply t, so that equation 7, 8, 9, the last 3 equations here, okay, the last 3 equations, you see each one has delta t. Here you have delta t, here you have delta t here, and then here you have v naught. So then they will change to the following. You see, your v will be equal to v naught plus at. V is equal to v naught plus at, meaning final velocity equals initial velocity plus acceleration times time. Then displacement is equal to the not displacement, final position of an object is equal to the initial position of an object. This means if I am using this one, I am not trying to find the displacement. Displacement is delta x, but x alone is final position of an object is equal to its initial position plus v naught t plus half at squared, and then final velocity squared minus initial velocity squared is equal to 2a. It should be delta x, but remember delta x is displacement, and displacement is final velocity, final position minus initial position. So instead of the delta x that I have here in equation 9, I can put x naught, where is it here? I can put x minus x naught. This is the measurement of delta x, so I can put it there. Now alhamdulillah, we will see solve problems on kinematics of blood circulation. Now let's look at the first problem. The first problem says, if the time taken for blood to travel through a vein is 10 seconds and the displacement is 1200 centimeters, what is the velocity? We are given the time taken, we are given the displacement, then we are asked to find the velocity. Okay, now first of all, you need to identify, you need to bring down the quantities you are given. In the statement of the problem, they say the displacement is 1200 centimeters. So you write 1200 displacement equals 1200 centimeters. Now, how long did it take to produce this displacement? In the problem, they say 10 seconds. So you now say, okay, my time is 10 seconds. Now they said you should get the velocity. So velocity is your target variable. You use the formula for calculating velocity, and the formula is velocity equals displacement over time. So if you look at, I didn't use symbols. If we go back to the velocity, this should be average velocity. You see, velocity is displacement divided by time taken. So I avoided using the symbol because I just want to make sure it is clear to everyone. Velocity, wow, there should be L here. Velocity, L is missing here. Velocity equals displacement divided by time. So the displacement is 1200 centimeters, the time 10 seconds, so you divide the two. In the next step, you just say 1200 centimeters divided by 10. When you take your calculator and press this, 1200 centimeters divided by 10, it will give you 120. Then you combine the units that you have here, centimeters per second. You see centimeters per second, and make sure you give space here. Don't attach the 120 to the centimeter. There should be a small space here. Okay, the next thing is, we know that the unit of velocity, the SI unit of velocity, is meters per second, not centimeter per second. So how do I change this centimeter to meter? I divide the quantity by 100. It will change this centimeter to meter. So you divide this 120 by 100. When you do that, you will get 1.2. So you now change this centimeter to meter, and now you have 1.2 meters per second. That is it. So we quickly move on to problem 2. Problem 2 says the velocity of human blood flowing through an artery is measured to be 30 centimeters per second. Now we are given velocity. Okay, let's identify what we are given. The parameters we are given in the problem. We are given the velocity 30 centimeters per second. What is the displacement of the blood after 5 seconds? So we are given the time taken, but our target variable is the parameter we are asked to calculate. Displacement is our target variable. So we bring down the velocity that we are given, the time, and then we move on to calculate the displacement. Here it is. We have velocity equals 30 centimeters per second, and then the time taken is 5 seconds. So our displacement will be velocity times time. Velocity times time. So your velocity is 30 centimeters per second, and your time is second. So you multiply 30 by 5. This will give you 150. If I multiply centimeter per second by second, you multiply the unit, then this second will cancel per second, and you will be left with centimeter. And this is why after multiplying 30 by 5, we got 150. Then we wrote centimeter. Again, the SI unit of displacement is not centimeter, it's the meter. So I have to change that. 150 centimeter, I will divide it by 100, and I will have 1.5 now in meters. So with this, I have completely solved the problem, and let's move on to problem 3. Problem 3 says a blood clot forms in an artery, causing the velocity of the blood flow to decrease from 20 centimeters per second to 10 centimeters per second in 2 seconds. What is the acceleration of the blood flow? Okay, remember, acceleration is change in velocity divided by time taken to produce the change. The velocity changes from 20 centimeters per second to 10 centimeters per second. How do I get the change in velocity? I will take the final velocity value and say minus the initial velocity value. The answer I get from that is the change in velocity, and the time taken to produce this change is 2 seconds. So I will just divide that change in velocity by 2 seconds to get my acceleration, my target variable. So here is the workings. Here is the working. Initial velocity from the problem is 20 centimeters per second. Final velocity from the problem is 10 centimeters per second. The time taken for this velocity to change from 20 to 10, okay, to decrease from 20 to 10 is only 2 seconds. So I now use this formula. Acceleration equals final velocity minus initial velocity divided by time taken. My final velocity is 20, so is 10. You see, I open bracket, 10 minus my initial velocity 20, I close the bracket, then centimeters per second. Why am I opening bracket and closing? is because they have the same unit. I don't want to write this centimeter per second twice, so I open bracket, close bracket, and put the subtraction inside, and then I put centimeter per second. It means this unit is for the two of them. Then divided by the time taken is 2 seconds. You see, so 10 minus 20 will give me minus 10. You see, here is the minus 10, and then I have this 2 under, so I have my 2. Then I will combine my centimeter per second with the second. It will give me centimeter per second squared, so we have centimeters per second squared. Okay, then minus 10 divided by 2 will give me minus 5 in centimeters per second square. Okay, even though we know that the SI unit of acceleration is meters per second square, not centimeters per second square, but we leave it like this because this acceleration is small. The acceleration is small. If I divide this by 100 to get it in meters per second square, it will be minus 0.05 meters per second square, which is a small value, so I can leave it like this and it's okay. Okay, problem 4. Problem 4 says a person's heart rate is 80 beats per minute. 80 beats per minute. What is their pulse rate? Meaning this person's in 1 minute his heart beats 80 times. So the question is, what is their pulse rate? So we need to know the meaning of pulse rate before we can find it. So here is the explanation. They say pulse rate is the number of times the heart beats per minute. The number of times the heart beats per minute, meaning how many times your heart beats in 1 minute. If you get that number, that is the pulse rate. And in the problem, we are told that this person's heart beat 80 times in 1 minute. It means the quantity that we are given is the pulse rate. So we are not calculating anything. We simply say that the heartbeat, the pulse rate is 80 beats per minute. But we have to give reasons for that. That is why we wrote few sentences before stating that. We say pulse rate is the number of times the heart beats per minute. It is an essential measure of heart health and can be felt by placing the fingers on the pulse point. Pulse rate is the heart rate, and then pulse rate is 80 beats per minute as we are given. Therefore, the person's pulse rate is 80 beats per minute without making any calculation. Okay, we say that pulse point, there are areas that we call pulse point. They are the areas in the body where you can feel the heartbeat. Or all arteries have a pulse, but are most easily felt at point where the vessel approaches the body surface, meaning where the arteries are close to the body surface, very close to the skin. Those are the points where you can get the pulse. Pulse points are shown in figure 4. You can see we have temporal, we have a carotid, we have apical here on the chest, we have on the neck, we have on the head here, we have brachial, we have radial, femoral, popliteal, you see, and then 2 down here, dorsal, pedal, and then posterior tibial. The 9 major points where the pulse can be felt. Okay, we now move on to problem 5. Problem 5 says a person's pulse rate is 100 beats per minute. What is their frequency? What is their frequency? So how do we get pulse frequency? How? Let's see that. In the solution, let us write what we are given. We are given the pulse rate. We are told that the person's heart beats 100 times in 1 minute. So their pulse rate is 100 beats per minute. Now here is the formula you can use to get the frequency. The frequency is simply pulse rate divided by 60. Now you may curiously ask where does this 60 comes from? It's not in the problem. If you read the problem, you do not have this 60. Nowhere this 60 is mentioned. Why are we using the 60? The 60 comes from this minute. They say 1 minute. So it is this 1 minute that you change to second. One per minute means for every 1 minute. So in 1 minute, how many seconds do you have? 60. So you want to get the number of beats in 1 second. That beat per second is what we call frequency. Okay, so frequency is pulse rate divided by 60. The per minute is changed to 60. So we have 100 for the pulse rate divided by 60, and then we get 1.67 hertz. The unit for frequency is hertz. This means in 1 second it beats nearly twice, because you can round up this one to 2. It's not up to 2, but we will say nearly twice. It's more than once. Okay, in 1 second. Okay, now let us go to the next segment of the program, which is flow rate. What do we mean by flow rate? We said that in the learning objectives that we are going to derive the continuity equation, and then we will use the continuity equation to calculate flow rate. Now the question is, what is this flow rate? We have to know this flow rate. We have to understand flow rate before we even begin calculating it using the continuity equation. Okay, here is the thing. They said flow rate, denoted by capital Q, is defined as the volume of fluid. When we say fluid, we mean liquid or gas. Anything that flows is a fluid. Okay, so solid cannot be a fluid because it's not flowing. Okay, so it's defined as the volume of fluid, V, capital V for the volume, passing by some location through an area A. A is the area of the location it is passing through during a time T, meaning after this time the volume that passes through that location is V. So now if I divide this V by T, it will give me the flow rate. That is why they say flow rate Q is defined as the volume of the volume V of fluid passing by some location through an area A during a period T. In symbols, this is how it is written. Q is equal to V upon T. If let's say, for example, I have a given point, maybe a given point on the artery, and blood flows through that point in 1 minute. After 1 minute, I get the volume of blood that passes through that point. So I will now get this volume, it's my capital V, and divide by the time in second. I will convert my time to second and now divide the volume by the time in second. This measurement will give me the flow rate of the blood at that point, where V is the volume and T is the elapsed time, meaning the time taken for this volume to pass. The SI unit for the flow rate is meter cube per second, and this is understandable because meter cube is the unit of volume and then second is the unit of time. You are dividing volume by time, so you will have meter cube per second. But a number of other units for Q are in common use. Okay, for example, the heart of a resting adult pumps blood at a rate of 5.0 liters per minute. So instead of this meter cube, you can also use liters as the unit of volume. Instead of second, sometimes we use the minute. Okay, so they gave an example that the heart of a resting adult pumps blood at a rate of 5.00 liters per minute, meaning in 1 minute the heart of a resting person will pump 5.00 liters of blood. So you have the flow rate in liters per minute instead of the usual meter cube per second. So note that 1 liter is equivalent to 1000 cm3. We have to understand this, because when we start solving problems, sometimes we need to convert the quantities we are given in liters to cm3 or meter cube. So 1 liter is 1000 cm3, and when this 1000, you can write it as 10 raised to the power of 3. This is why we say 10 raised to the power of 3 in cm3. Again, if sometimes you may need to change from liters to meter cube. So if I have quantity in liter and I want to change it to meter cube, I will simply divide it by 1000. 1 divided by 1000, so I have it in meter cube, and 1 divided by 1000 is simply 10 raised to the power of -3 from indices. So you can either divide the quantity by 10 raised to the power of -3, or you multiply that quantity by 10 raised to the power by 10 raised to the power of -3. Let me say that again. If you have a quantity in liter and you want to change it to meter cube, you have two options. The first one is divide it by 1000. You have fully converted it to meter cube. The second one is to multiply that quantity by 10 raised to the power of -3. You have again fully converted it to meter cube. Okay, now the continuity equation. We say that the continuity equation describes the motion of a fluid through a system as its mass is conserved, meaning you have matter like liquid or gas passing through a system, and then no quantity of that matter is missing. That is the meaning of mass is conserved. Okay, mass is conserved. No quantity is missing. All of it remains the same, and no quantity is added. That is conservation of mass. So when you have that system, we say that we have an equation that can describe the motion of that system. It is used on a variety of objects, including tubes, pipes, rivers, and ducts that carry gases or liquids. Look at what we're talking about here. Look at the diagram that that will help us here. You have a pipe. This one, the diameter or the cross-sectional area is large, and this one, the cross-sectional area is small. So I have, let's say, a liquid. It can be water, it can be blood, flowing through here. Okay, it flows through here, and then when it enters here, it also flows through here. All of it flows. All of it flows. No mass is missing, and no mass is introduced apart from what we have here. So the mass is conserved. We say that we can have an equation that can accurately describe the motion of this system in terms of the velocity of the fluid and the cross-sectional area of the path it follows through a cylindrical pipe with different cross-sectional areas A1 and A2. Okay, let's see how we can derive the continuity equation using figure 5. Which one is figure 5? This is figure 5. So we will return to this diagram again and again. This is, suppose an incompressible fluid flows through region 1. Where is region 1? You see this region, they call it region 1, and this region here, the small one, they call it region 2. So let's assume an incompressible liquid flows through region 1. And what do we mean by incompressible liquid? If we say a liquid is incompressible, we mean its density is constant. Its density is constant. That's the meaning. So if you have a liquid with constant density flowing through region 1, and the region 1 has cross-sectional area A1, and then the speed of the fluid in that region 1 is V1, and then the time taken by that liquid to flow through region 1 is T seconds. Let's assume that you have incompressible liquid with constant density flowing through region 1. The cross-sectional area of region 1 is A1, and the speed of that liquid in region 1 is V1, and the time taken for this liquid to flow in region 1 is t seconds. If the distance moved by the liquid through A1 is d1. Again, the distance moved, let's go back there. The motion started here, okay, and it ended here. So if we call the distance from here to here, this distance, if we call it d1, and the time taken to produce this distance is t. The cross-sectional area is a1, and then you can see v1 is the velocity of this incompressible liquid in region 1. Everything shown except the d, of course, except d1. Then the volume of the liquid v1 is, the volume should be a1 d1. Why do we say volume is a1 d1? Because this is a cylinder, okay. If consider this one is a cylinder, and if you want to get the volume of a cylinder, you take the cross-sectional area and you multiply it by the height. Since this is lying down, the distance becomes the height. If you just take this portion here and then go down here and then down here and then come here, this is a cylinder. You have the cross-sectional area here, and then from here to here is the height, okay. The distance is the height. So if I multiply the area by the height, it will give me the volume, and this volume is the volume of the liquid passing through it, the volume of the cylinder. Why? Because the liquid takes the shape of that cylinder. Liquid has no fixed shape, it only takes the shape of the container. So we use the volume of the container to calculate the volume of the liquid. That is why we say v1 is a1 d1. Again, we also know that the density of any substance is mass of the substance divided by the volume. So the mass of the liquid M is, meaning the mass, the entire mass here, let's go back here, the entire mass of the liquid that we have in this region, we can look at it here. From this equation, we know that mass is density times volume. But remember, the volume, we called it V1. So we are going to multiply the density by V1. So our mass of the liquid is equal to density multiplied by V1. And if we look at equation 14, we say that V1 is A1 D1. So instead of V1 here, we can put A1 D1, and this is why we say is equal to rho A1 D1. And let's call this equation 15. Okay, now this is what we can do for this region where we have A1. Assuming the liquid now enters region 2 here. If the liquid enters region 2, what happens? Let's hear what they say. They say at the same time, the liquid also flows through a region, meaning the time it takes to flow through that region, it also takes the same time to flow through region 2, okay, of cross-sectional area A2 with speed V2, meaning the time it takes to flow from here to here, it takes the same time to flow from here to here in region 2. And you see it covers a larger distance, and then the area here is smaller compared to the area we have here. So we have A2 here, and then its speed is V2 now, not V1. So what are they going to say now? But remember, the mass is constant. The mass is constant. The mass is constant. There is conservation of mass. So they say the mass of the liquid through this region is, we do not call the mass M2, and we didn't call that first mass M1, because the mass is the same. There is conservation of mass in the process. So our mass is the density times the volume in that region. So the volume in that region will be A2D2. In the same way, we found the volume in region 1 as rho A1, sorry, A1 D1. So that one will also be A2 D2, and it's a cylinder. Look at the cross section. If you take this is the cross section, and then if you go down here, okay, and then come to 2, and then come back here, just this shape, you can clearly see that it is a cylinder. If I take this up, let's say this one is up and this one down, then the distance from here to here is my height, and the volume will be cross-sectional area times height. So the height is just the distance, the new distance, let's call that distance d2. So the volume will be a2 d2, and this is why we have it here as our where is it? I have v2 a2 d2, rho a2 d2. So they say provided that the liquid is incompressible, meaning the density of the liquid is constant, then the two masses are equal. And if the two masses are equal, we can write this. The first mass, we express it as rho a1 d1. The second mass, we express it as rho a2 d2. It means we can equate the two. The two are the same. So we can say, we can write this as rho a1 d1, the first mass, is equal to the second mass, rho a2 d2. And clearly you can see that if I divide both sides by rho, by this rho, the rho I have here cancels the rho I have here. Why did I not put rho 1, rho 2 here? Because I have the same liquid. If it is water that flows through region 1, it's the same water that flows through region 1. And we know that density, if the liquid is the same, the density will not change. The density will not change. So this is why we do not put rho 1, rho 2, so that the two can cancel. They are identical. We now say cancelling rho on both sides of equation 17 yields, then we have a1 d1 and a2 d2, because rho has been cancelled. Okay, the next idea is that, remember, the time taken to produce this volume is the same time it takes to produce this volume. So we can divide both sides by that amount of time, same amount of time. Dividing both sides of equation 18, this is equation 18, by the time taken t yields, okay, if I divide this by t, if I divide this one by t, it will be distance over time. This one will also be distance over time. So distance over time will be speed. Okay, here too, distance over time will be speed. And this is why here we say E1 V1. Because when I divide D1 by T, it gives me speed. It becomes V1. This one too, D2 by T, will give me V2. You see, that is why they said where V1 is D1 upon T and V2 is D2 upon T. Equation 19, which one is equation 19? This equation, A1 V1, cross-sectional area in region 1, speed of the liquid in region 1, is equal to cross-sectional area in region 2, speed of the liquid in region 2. This equation is the continuity equation. So you see, we have derived the continuity equation. Very simple, and is valid for any incompressible liquid, meaning it is true, it is applicable to all incompressible liquids, no exception. When we say incompressible liquid, in bracket, they tell us the meaning. They said a liquid whose density is constant. However, in many situations, including the cardiovascular system, branching of the flow occurs. Sometimes, the path, if you look at the diagram we use, there is no branching. You have a single path, okay, with big cross-sectional area, and then it enters into a single path with cross-sectional area smaller than this. So what they are saying is that sometimes you can have so many branches here coming. Let's say I have like 5 pipes, and all of them, the same liquid comes from each of the pipe, and then they enter here, and maybe this one also is split into 10 different pipes. So you see clearly there is branching. How do we solve this problem? That is what they are telling us. What do we do? They say in cardiovascular system, definitely, because we know in the body we have so many branching of the arteries, branching of the veins. Okay, so this is why they say, however, in many situations, including in the cardiovascular system, branching of the flow occurs. See figure 6. Where is figure 6? Clearly, can you see? We have this artery, and there is branching here, and then to arterial, and then from the arterial, look at it, you have 1 2 3 branches, and then if you take this branch, you see it's divided into 2 branches, and then this one too is further divided into 2, and on and on. So how do we solve this problem? How do we solve this problem? The meaning, or in other words, how do we write the continuity equation in a way that it will take care of that situation, having more than one path? The blood is pumped from the heart into arteries. You see so many branches of the arteries that subdivide into smaller arteries, which they call arterioles, which branch into very fine vessels called capillaries, as we can see in this diagram. So what do we do? They say in this situation, continuity of flow is maintained, but it is the sum of the flow rate in each of the branches in any portion along the tube that is maintained. Okay, let me explain that using the diagram. Let's say I have this one, it enters here. I have blood here. The flow rate that I have here is divided into 3 because of the branches that I have. So if I get the flow rate here, and then plus the flow rate here, plus the flow rate here, will give me the flow rate that I have here. Now, the flow rate that I have here, we see because of the branching, I have 2 branches here, is split into 2. Each one has its own flow rate. So if I get the flow rate here plus the flow rate here, it will give me the flow rate that I have here. That is what they are saying. Again, when it enters here, the venue, now the flow rate that I have, because the blood flows like this, okay, when it enters here, the flow rate that I have here is the total flow rate in the branches that I have here, plus here, the 3 branches. They combine, I get the 3 flow rate and add them together to get the flow rate that I have here. That is what they are saying. If again I have this, let me count this 1 2 3 4, maybe 5, maybe 6, maybe 7, maybe 8, 9, 10 on one side, and then on the other side I have 1 2 3 4 5 6 7 8 9. Then on the left hand side I have a number, on the right hand side I have a number. So I will put those numbers in my equation, and you will see how it will change too. They say the equation of continuity in a more general form becomes, can you see, this is the number on the left and this is the number on the right, meaning number of the branches that you have. You put it here, nothing is changed. You see my A1 B1 A2 B2 is still the same. I only added N1 here and N2 here, meaning I have the number of branches that I have in region 1, and this is the number of branches that I have in region 2. Where N1 and N2 are the numbers of branches in each of the sections along the tube. The continuity equation shows that as an incompressible liquid flows from a region of large cross-sectional area to a region of small cross-sectional area, as seen in figures 5 and 7, its average speed increases. Okay, When the area decreases, the speed will increase, and when the speed increases, the area will decrease. The area and the speed are in inverse proportion. If one of them increases, the other will decrease. And we can understand this from this diagram here, and this is why it has to cover larger distance. Can you see here? Because the area is large, the speed is small, and this is why it covers just small distance here. But here the area is small, so the speed will be high, and that is why it covers a larger distance. This is what they are trying to tell us, that the speed and the area are in inverse proportion. If one of them is high, the other one is low. Okay, let's go back and continue. What a lovely discussion. Very interesting. Okay, look at this one. I have this is the figure 7 they are talking about. Look at this region. It's a very large region, and I have the area as A1 and the speed is V1. So they are saying because this A1 is large, the speed of the liquid here is small. But now that it has entered a region with small cross-sectional area, the speed will increase. As the liquid passes through here, it will move faster. That is what they are saying. But this holds if my number is 1. Can you see? Because I have one branch here, I have two branch here. What if I have more than one branch? Okay, more than one branch. We will see that later and see how it changes. We will see that in problem solving, inshallah. When the cross-sectional area of the tube decreases from A1 to A2, the average speed of the fluid increases from V1 to V2. Now, okay, there is another way we can express flow rate, the Q, the capital Q. If you look at this equation, where is it? And this one, we don't have flow rate here. Flow rate is denoted by capital Q. But you can say the first observation you can make is that I don't have Q here. What if I want to get flow rate using these quantities? How do I go about it? Okay, so this diagram, using this diagram, we can show you how to do that. You see this diagram? So lovely. Okay, if you look at this diagram, I have a liquid that flows from here to here. Okay, so the distance traveled by the liquid along the tube from here to here is D. The cross-sectional area of my cylinder is A. So the volume is AD, as we explained earlier. Take cross-sectional area, multiply it by this distance, you will get the volume. So if I want to get this velocity, this V is the velocity, not the volume. Okay, the vector, there should be arrow here, but they didn't put it in the diagram. Anyway, so the velocity, meaning this velocity or speed of flow, is equal to the distance divided by the time. The distance divided by the time. This distance and the time it takes to flow from here to here. Now, remember again that your flow rate is volume, meaning the volume of this entire liquid colored red, okay, divided by the time it takes this liquid to move or to flow from this region to this region. So you have V divided by T. Okay, V is the volume. Remember, we say the volume is A times D. So you have A times D as the volume divided by time. So if you look at this one, can you see D over T? Just this D and T. D upon T is what you have here, D upon T as the velocity. So it means I can take this A, instead of D over T, I can put V there. So I have AV. And this AV is what I have here in the equation. This is what I have. Let's go back to the one without the branching. Can you see? It means this A1V1 is the measurement of the flow rate. Is the flow rate in region 1, and this one is the flow rate in region 2. Wow, mathematics is so beautiful. It will help you understand complex concept, complex phenomena. And clearly we have understood this. So our EV is the flow rate. So flow rate through a cylindrical pipe of cross-sectional area A. Also figure 8. Which one is figure 8? This figure 8. Okay, they are trying to give us this explanation. Figure A shows that the flow rate Q is proportional to both the cross-sectional area and the average speed. It means if any of these quantities A and V changes, it will affect this Q. And if any of them increases, the Q will increase. And so we can write the flow rate as Q is equal to AB. Okay, so this means, remember, we have two formulae for flow rate. The first one is Q is equal to V upon T. V upon T, look at it. Q is equal to V upon T. So if I am given the volume of the liquid and the time it takes to flow, I can divide that volume by T to get the flow rate. Unfortunately, in most cases, I will be given the area of the path, the cylindrical path the liquid flows through, and then the speed of the liquid in that cylinder. So I will simply multiply the two to get my flow rate. So this equation is more frequently used compared to the earlier one. Since liquids are essentially incompressible, the equation of continuity is valid for all liquids, because when deriving this equation, remember, we assumed that the liquid or the fluid is incompressible. The liquid is incompressible. Okay, so if it is incompressible, and we know that generally in most instances we can't say all, okay, but most liquids are incompressible, and because of that, this equation is valid for nearly all liquids. But for gases, we know that gases are compressible. Even though we use the equation for gases, but we use those equations carefully. So the equation must be applied with caution to gases if they are subjected to compression, because sometimes we can compress a gas, of course, and a gas can expand. And if there is compression or expansion, density is no longer constant. Why did I say that? Density is mass over volume. If I compress a gas, the volume changes, and if the volume changes, the density will change. If a gas expands, the volume increases. An increase in volume will decrease the density of the gas. So you can see that under compression and expansion, the density of a gas is not constant, and in that situation we do not use the continuity equation. We do not apply it at all. Alhamdulillah. Now we are going to solve problems. Here are solved problems on flow rate Q and the continuity equation. Problem 1 says determine the blood flow rate in a capillary with a cross-sectional area of 3 times 10 raised to the power of -5 meters squared and a speed of 0.5 millimeters per second. Okay, as I explained previously, that we do have two formulae for calculating flow rate. The first one is volume divided by time, and that is when I am given the volume and the time it takes for that volume of liquid to pass through a given area. But that formula is not common. The other one, Q is equal to AV, cross-sectional area, times the speed of the liquid in that area. That is the one that is common. We have to take note of that. And we can see in this problem, we are given the cross-sectional area, and we are also given the speed. The formula says we should multiply the two to get the blood flow rate. So the first thing we do is to bring out the parameters we are given. So solution, you are given the area, so you write area comma a equals, this is the quantity you are given, and you are given this quantity in meters squared. Okay, meter squared is the SI unit of um, of area, so no conversion is needed here. But the speed is given in millimeters per second. The speed given, you see, where is the speed? 0.5 millimeters per second. So it says speed v is equal to 0.5 millimeters per second. But since this one is meter that you have here, these millimeters must be changed to seconds. So here is the idea. The first m that you see here is milli. The second m is the meter. It means you are going to keep this second m, and then you get rid of this m, the first m. How do you do that? You simply multiply by 10 raised to the power of minus 3, because milli means 10 raised to the power of minus 3. So this is equal to 0.5 times 10 raised to the power of minus 3. This is your first m, and then you keep the second m for the meter per second. So now there is unit consistency, meter here and meter here. So the next thing is to write the formula for calculating the flow rate. Flow rate Q equals AV, and your A is this quantity. Can you see this quantity? So you put that in bracket, 3 times 10 to the power minus 5 in bracket. In the second bracket, you put your speed, the converted speed, not this one. If you put this one, you are wrong. You put the converted one, 0.5 times 10 to the power minus 3, and this is what you have. So you press your calculator, 3 exponential negative 5 multiplied by 0.5 exponential negative 3. This will give you 1.5 exponential negative 8. Then how do I get the unit for flow rate? I multiply the two units, meter squared times meter per second. Meter squared times meter will give me meter cube. So I combine this with the per second. I get meter cube, or cubic meter per second. So this is what I have, cubic meters per second. The second problem here, the second problem says, if the blood flow rate in an artery with a cross-sectional area of 10 raised to the power of minus 4 square meter is 1.5 times 10 raised to the power of negative 3 cubic meter per second. What is the speed of blood flow in the artery? You have blood flowing through the artery. You are given the flow rate. This means this quantity is my Q, and then you are given the cross-sectional area of the artery. This is my A, but you don't know V. Okay, your target variable is V. So let's see how we can get that. First of all, bring out the parameters you are given. Here is the area, and here is the flow rate that you are given. Then your target variable, the quantity you are asked to get, is the speed. So here is the formula for calculating flow rate. From here, if I want to get the speed, I will divide my flow rate by the cross-sectional area. If the cross-sectional area, if it is the cross-sectional area I want to find, again I will divide my flow rate by the other quantity V. But now I want to get V, so I will divide Q by A. So my V equals Q divided by A. Here is my Q. I will take it and say divided by the A. So when I do that, look at my Q here and look at my A here. Now you take your calculator and say 1.5 exponential negative 3 divided by 1 exponential negative 4, and this will give you 15. Now how do you deduce the unit of velocity from the two units here? You see, the meter squared will cancel 2 meters here. Here is like meter times meter times meter, 3 of them, and here you have meter times meter, so the 2 will cancel the 2 here, and you still have 1 meter remaining, then per second, and that is the unit of velocity. So velocity, you obtain the velocity in as 15 meters per second. Then we move on to problem 3. Problem 3 says a person has 5 arteries in their leg, each with a cross-sectional area of 2 times 10 raised to the power of minus 4 square meters. If blood flows through each artery at a speed of 1.2 meters per second, what is the total blood flow rate in the leg? What is the total blood flow rate in the leg? Okay, this is interesting because we have branching here. Remember what we said about branching? We are given the number of arteries here, and then each artery has this cross-sectional area, and then the speed of the blood in each artery is this, and we are asked to get the total flow rate. So the total flow rate is the total flow rate in all the 5. You get the flow rate in this, in the first one, the second one, the third one, the fourth one, and the fifth one. And since they have identical cross-sectional area, they have identical speed. Okay, so when we multiply the area by the speed, we will get the the flow rate in each of them. Then we multiply by 5 to get the total. That is what we will do. So here we bring out the parameters. We are given number of arteries is n is equal to 5, and then cross-sectional area we are given as 2 times 10 to the power of minus look at it here, minus 4 in square meter, and then the blood speed in each artery is 1.2 meters per second, and so total blood flow rate is equal to, we see Q is equal to AVN. AV is the flow rate in each artery. Then we are multiplying by n, where n is the number of arteries. If you like, you can put this n here, NAV is still the same. So it means we are going to multiply the two. Here, our A is this, and then our V is this, and the number is 5. So when you multiply all of them, take your calculator and say 2 exponential 4 multiplied by 1.2 multiplied by 5, and you will get 1.2 exponential negative 3. Then multiply the unit, the 2 unit. This is just a number, it has no unit. So you multiply the unit of area by the unit of speed to get the unit of your flow rate. Meter squared multiplied by meter per second, meter squared times meter cube. So I will get meter cube per second. So with this, I completely solved problem 3. Moving on to problem 4. Problem 4 says the aorta. I love problem 4 so much. The aorta is the principal blood vessel through which blood leaves the heart to circulate around the body. We saw that in our explanation of the kinematics of the blood flow. This is just a background information. We call it background information. Okay, they are giving you background information to help you understand the situation before you start solving the problem. A, here is the first question. Calculate the average speed of the blood in the aorta if the flow rate is 5.0 liters per minute. The aorta has a radius of 10 millimeters. Okay. This is interesting. They want us to get the average speed of blood in the aorta, and we are given, this means we want to get V. They want us to get V, and we are given the flow rate of the blood in the aorta in liters per minute, and then we are not given the area. Instead of giving us the area, they gave us radius. So let me make this general statement. It is very helpful. Whenever they mention radius or they mention diameter, they want you to use that area or that diameter to calculate cross-sectional area. Okay, let me repeat that. Whenever they give you radius or they give you diameter, they simply want you to use those quantities to get your cross-sectional area. So from here we will get the cross-sectional area. and then this is our flow rate, but the flow rate is not in meter cube per second, it's in liters per minute. So we will change this to meter cube per second, and then we now use the flow rate equation to get the speed we are asked to find. Then here is the second problem. They say blood after leaving the aorta, blood also flows through smaller blood vessels known as capillaries. When the rate of blood flow in the aorta is this, you see, they still maintain this value. The flow rate in the aorta that is mentioned earlier is still now is mentioned again. The speed of blood in the capillaries is about 0.33 millimeters per second. We can see that the speed is very small. This is the speed in the capillaries, not in the aorta. Okay, in the aorta, we are asked to find that. Given that the average diameter of a capillary is 8.0 micrometer. Remember what I said. When they give you radius or diameter, they want you to use that to evaluate the cross-sectional area. Calculate the number of capillaries in the blood circulatory system. Okay, let us begin. Where we will begin from here. Okay, we will change this one to meter cube per second, and then this radius we will use it to get the cross-sectional area, and then we use the two quantities to get our average speed. Let's see the solution. In the solution, we are given the flow rate Q 5.0 liters per minute. Now this means 5 liters divided by 1 minute. Change this to 5 liters divided by 1 minute. Then liter, we have to change it to meter cube. And previously we said to do that, we simply multiplied by 10 raised to the power of minus 3. And then 1 minute, we know is 60 seconds, so we just put 60 seconds there. So you see, we change this 5.0 multiplied by 10 raised to the power of minus 3. Once we do that, we can change L, we can remove L and put meter cube. We have changed it. And then the 1 minute here, we write 60 seconds in its place. So if we take our calculator and do it, calculator 5.0 exponential negative 3 divided by 60 will give you approximately 8.33 times 10 to the power of minus 5, and then you now combine these two, you need meter cube per second, and that is your flow rate in meter cube per second. Then you now come to the aorta radius. You are given the radius at 10 millimeters. Remember what we said earlier, that the first m is milli and the second m is meter. So this milli is 10 raised to the power of minus 3. So you simply say this 10 that you are given times 10 raised to the power of minus 3, this is your milli, and then the last m is meter, so you keep it. Now you have changed this to meter, and then this one also, you see there is unit consistency. Next, you use this to get you use R1. Why did we call our radius R1? Because this is the radius in the aorta, and we are also going to use the radius in the artery. So we have to differentiate the two radii. Okay, aorta cross-sectional area, this is the formula you use to calculate the aorta cross-sectional area. A1, okay, is equal to pi R1 square. Pi R1 square. Your R1 is this. Pi is a constant, so it means my A1 is pi. This is my R1, the one I converted here, my converted R1. I put it here with the unit, I close bracket. So if I press my calculator, pi open bracket 10 exponential negative 3 close bracket, I put the square, it will give me this value, and then this square will affect my m, and it will become m squared. So I have A1 equals this. I got my A1. So I got my A1, I got my Q. Now I can get my V, velocity or speed in the aorta. So Q is equal to A1 V1. I want to get V, so I will multiply Q by, I will divide Q by A1. So V1 equals Q upon A1. So moving on, my Q, I got my Q here from the above, and I got my A1 from the above, you see. So if I take my calculator and say this one divided by this one, it's gonna give me 0.265. And then how do I deduce my velocity? Again, this m squared will cancel 2m here, remain 1m, so I have meter per second. You see the velocity in the aorta is just 0.6265 meters per second, which is 26.5 centimeters per second. So now I know the speed in the aorta, and I also know the cross-sectional area of the aorta. Now, the second problem, let's go back to the second problem. What exactly do they want us to find? They say we should the speed of blood, calculate the number of capillaries. Okay, it means here we will have to get the velocity, the cross-sectional area, we multiply the two, and then we apply the general formula. So let's see that. So diameter of a capillary, we are given the diameter in the second part of the problem as d is equal to 8.0 micrometer. Now from the diameter I can get the radius. The radius of a capillary R2 is equal to diameter, divide this diameter by 2. Why? Because 2 radii will give you the diameter. So if you have the diameter and you want to get radius out of it, divide the diameter by 2. So your R2 equals d upon 2. R2 is the radius of the capillary. Remember, we use R1 for radius of the aorta. So my diameter is 8.0, and then I divide this by 2. When I do that, my R2 is 4.0 micrometer. And this micro here, this symbol that you see, this Greek letter micro here, means 10 raised to the power of minus 6. So I can change this to meter. I will just say 4.0 times 10 raised to the power of minus 6. So you see, it's equal to 4.0 times 10 raised to the power of minus 6. This one is my micro. Okay, now I know the radius of the artery. Next, I need to know the cross-sectional area of the artery. I will use this radius to get the cross-sectional area. So cross-sectional area of a capillary, A2 is equal to pi R2 squared. Okay, pi R2 squared. So then I will now make substitution. My A2 equals pi, and my R2 is the one I just calculated here, this converted one. So I will put it here with the unit, and then I square it. Now if I press this in my calculator, I will get 5.0265 times 10 to the power of negative 11, and then the square will affect my unit and it becomes meter square. So I know the area here, and I also know diameter. From the diameter I got the radius, from the radius I got the area. So what about the speed? I am given the speed already from the problem, but the speed is not in the SI unit. They say that the blood speed in capillaries V2, we call it V2, equals 0.33 millimeters per second. Remember, this first m milli, the first m here milli, is 10 to the power of minus 3. So you convert that 0.33 times 10 to the power of minus 3, and now you are left with 1 m per second, so meter per second. So now you can use the general formula. Okay, remember this one, you apply the left hand side to the aorta, because you are told that the blood flows from the aorta to the capillaries. So if that is the case, from the aorta to the capillaries, we know that we have only one aorta. So my N1 is just 1. My N1 is equal to 1 because I have one aorta. So this A1 V1 becomes the flow rate in the aorta. So I can just put Q for that because I already know the flow rate in the aorta. I calculated that. Where is it? Okay. Look at it here, flow rate in the aorta. they gave me the flow rate and I changed it to they gave me in liters, in liters per minute, and then I changed it to meter cube per second. So this is the one that I need, 8.33. Okay, let's go down again. So this one becomes Q, and then in the capillaries my N2 becomes the number of the capillaries, and then A2 cross-sectional area of the capillaries. Each capillary has this cross-sectional area, and then V2 is the speed of blood in each capillary. So, and they want me to get this number of capillaries, N2. So Q is equal to N2 A2 V2. If I want to get N, I will divide Q by the remaining 2, A2 V2. So therefore my N2 equals Q upon A2 V2. The next thing is I will substitute the values here. For Q, this is the value in meter cube per second. For A2, you got the A2. Where did I get? And this is my A2, 5.026 times 10 to the power minus 11. So you put that. You see it here. And then this next, you now put V2. Where is V2? Look at V2. You got it, 0.33 times 10 to the power minus 3. You put it here. If you evaluate this correctly, you will get 5.0 times 10 to the power of 9 capillaries, meaning you have about 5 billion capillaries. 5 billion. The number of capillaries is 5 billion. This one is an approximated one, and definitely is more than 5 billion. It's about 5 billions with about 200 million capillaries. Of course, here they said, I like the final statement here. Yeah, but before that, this number, we need to ask ourselves whether this number makes sense or not. Okay, the number of capillaries getting to about 5 billion, it makes sense because our skins or our bodies are made up with billions of capillaries. That is why when we get a cut, the blood easily gushes out. Capillaries are being cut. Okay, so if we have a single number, let's say we just have 10 or 5 or 20 as the number of capillaries, no, it means our answer does not make sense. It contradicts reality. The number of capillaries, okay, if the aorta supplies blood to the capillaries, those capillaries have to be enormous, large. The number has to be enormous. So that is why this number makes sense. Now, note that the speed of flow in the capillaries is considerably reduced relative to the speed in the aorta. Meaning, if you consider the speed when the blood leaves the aorta and enters the capillaries, the speed is very small. And we are given that speed. If you look at it, look at the speed we are given, 0.33 millimeters per second. The speed is very, very small. Very, very small. This means the blood is not fast flowing in the capillaries. Considerably reduced relative to the speed in the aorta. Why? They say due to the significant increase in the total cross-sectional area of the capillaries. Okay, what they are trying to say is that let me go back to the equation here. Okay, here if I multiply n by a, these billions that I have, if I multiply it by a, it means my cross-sectional area has increased. I remember what we said, the area and the speed are in inverse proportion. If one of them is large, the other one is small. So if you get the total cross-sectional area of all the capillaries, you add them together, the capillaries are in billions. If you multiply the cross-sectional area of one capillary by their number, you will get a very large number, large quantity. So that quantity tells you that the cross-sectional area is large, and because the cross-sectional area is large, the velocity will be small, considerably small. So mathematically, this is how it came about. But does it have any medical implication? They say this low speed is to allow sufficient time for the effective exchange to occur, so that the exchange of nutrient, the exchange of oxygen, because the blood carries oxygen to the body part. So when it meets the body part, it has to move slowly so that there will be effective exchange of oxygen and nutrient. Okay, not that it is fast moving. No, 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 no. Although it is equally important for the flow not to become stationary, to avoid the possibility of clotting. At the same time, we don't want the blood to stop flowing. Of course, it is advantageous for the blood to flow slowly, but we don't want the blood to stop flowing. We don't want it to come to rest, because when it comes to rest, there will be possibility of clotting, and we don't want that. This is what they are saying. Here are a few problems evaluation. After watching this video, you should be able to answer these questions. Question number one, I call it evaluation, to test your level of understanding of the topic. Give a brief account of the kinematics of human blood circulation. Question 2. A person's heartbeat is 6,000 per hour, 6,000 beats per hour. What is his pulse rate, and then what is his frequency? Okay, here are all the questions here. Look at the questions. Number 3, and then we have number 4 here with A and B. Number 4, they want you to derive this formula A1 V1 A2 V2, which we did earlier, and also define blood flow rate. Okay, and then number 5, a person has 5 capillaries. This one they want you to use the general formula for the continuity equation. And then number 6, the blood flow rate in a capillary with a cross-sectional area of this is this. You are given the flow rate, you are given the cross-sectional area, and they want you to get the speed of the blood in the artery. Alhamdulillah. When you finish that, the questions that require calculation, I gave you the answers here. Number 1, number 2, A and B, here are the answers. Number 3, this is the answer. Number 5 and number 6, you either express the answer like this in meter per second or in millimeters per second. It's correct, because the speed you can see is very small. Alhamdulillah, Alhamdulillah. This is the end of our today's of this week lesson. Alhamdulillah, may Allah grant us beneficial knowledge. Assalamu alaikum wa rahmatullah.